Welcome to the Bullvine Podcast, your go-to source for inside stories, cutting-edge research, and the latest updates in the world of dairy farming. For the 72nd episode, we explore how understanding the genetics of plasma biomarkers enhances dairy cow resilience. So please grab a glass of milk, sit back, and let's get started with this week's episode.
In the dynamic world of dairy farming, cows must be resilient to withstand challenges such as lactation cycles and environmental stressors. Metabolic stress poses a significant threat, impacting not only animal welfare but also milk production and fertility, making the transition period particularly critical. Plasma biomarkers as potential endophenotypes offer insights into cows' genetic stress responses, enabling farmers and scientists to breed stronger, more resilient herds. This genetic understanding heralds a new era of sustainability for the dairy industry.
In understanding the complexities of resilience in dairy cows, genetics play a significant role in controlling plasma biomarkers, which are key indicators of how well an animal can manage metabolic stress. These biomarkers, such as perioxenase and guanine-glutamyl-transferase, essentially act as the biochemical checkpoints of a cow's health status, revealing how efficiently the animal copes with metabolic upheavals. Genetic influence on plasma biomarkers. The genetic control of plasma biomarkers is akin to having a roadmap that dictates how these biochemical signals are expressed, indicating an animal's intrinsic ability to withstand stress. When dairy cows face the high-demand nature of the transition period, their bodies undergo significant physiological stress. The steady control of these biomarkers suggests a robust genetic framework that supports optimal health and performance. For instance, genetic variations detected by genome-wide association studies, GWAS, have shown specific loci associated with higher resilience traits on chromosomes. These studies have expanded our understanding of how genetic predispositions can impact the expression of crucial biomarkers directly linked to stress responses. Thus, focusing on these genetic factors offers a window into enhancing inherent resilience, paving the way for breeding programs that aim to fortify livestock against stress-induced challenges.
The concept of endophenotypes is a critical tool for unraveling genetic complexity. Endophenotypes are measurable components inside an organism that bridges genetic predispositions and broader phenotypic traits, like stress response. Essentially, they are simpler to quantify than the overall trait and are often controlled by fewer genetic variables, providing more precise insights. This approach demystifies the genetic study of complex traits by narrowing the focus to specific, heritable markers that offer reliable indicators of broader phenotypic attributes. By identifying and targeting these endophenotypes, researchers can more effectively dissect the intricate genetic architectures that govern resilience, ultimately leading to more informed and strategic breeding decisions. The interplay between genetic control over plasma biomarkers and the strategic use of endophenotypes is central to advancing the dairy industry's quest for more resilient cattle. As we deepen our genetic understanding, the opportunity to enhance livestock's ability to handle stress becomes ever more practical and attainable.
As we delve into plasma biomarkers, we step into a new frontier of understanding dairy cow resilience. The study highlights 4 key biomarkers: perioxenase, guanine-glutamyl-transferase, alkaline phosphatase, and zinc. Each plays a pivotal role in the stress response mechanisms within these animals. Perioxenase, for instance, acts as a sentinel against oxidative stress. This enzyme helps to protect lipoproteins, which are essential for all cellular functions, from oxidative damage. Lower levels of perioxenase are reported to be linked to increased oxidative stress, which can impair milk yield and affect overall reproductive performance. By monitoring perioxenase levels, farmers can gain insights into an animal's oxidative status, thus shaping strategies to mitigate stress-related declines in productivity. Guanine-glutamyl-transferase, GGT, is a critical indicator of liver function and is involved in glutathione metabolism, an antioxidant. Elevated levels of this biomarker often signal liver stress or damage. In the rigorous conditions of early lactation, high GGT levels can paint a picture of the biochemical strain endured by the animal. GGT not only acts as an alarm for potential liver issues, but also highlights a dairy cow's ability to endure and adapt to metabolic challenges. Alkaline phosphatase is widely known for indicating bone health and metabolic activity. In the context of dairy cows, this biomarker gives additional insights into the stress response linked to bone metabolism, particularly among primiparous cows still maturing. By regularly checking alkaline phosphatase levels, farmers can make more informed nutrition and health management decisions, optimizing a cow's ability to handle metabolic stresses. Lastly, zinc, a simple trace element, is a cornerstone of immune competence and stress resilience. It is crucial for maintaining the structural integrity of cell membranes during stress. Low zinc levels can predispose animals to infections, prolonging recovery times. Understanding zinc dynamics provides a glimpse into the cow's resilience and capability to ward off infections under stress. Collectively, these biomarkers do more than reflect current health. They act as predictive resilience tools. By integrating biomarker monitoring into regular herd management, dairy farmers can improve individual animal welfare and enhance overall herd productivity and longevity. As this frontier expands, the evidence becomes compelling. Embracing genetic insights can pave the way for a robust, resilient future for the dairy industry.
Genome-wide association studies, GWAS, are powerful tools in the scientific arsenal, offering deep insights into the complex genetic architecture underlying various traits, including metabolic stress response in dairy cows. In the study under review, GWAS was employed to traverse the genetic terrain mapped by 739 healthy lactating Italian Holstein cows. By analyzing 88,271 genetic variants, researchers unearthed significant associations that spotlight the genetic variants linked to 4 critical plasma biomarkers: peroxynase, glutamyltransferase, alkaline phosphatase, and zinc. The methodology behind GWAS in this research is both rigorous and expansive. The process begins with collecting genetic data via DNA extraction and subsequent genotyping using advanced SNP arrays. These genetic markers serve as the baseline for the study, mapping out the genomic landscape. The data is rigorously filtered for quality, ensuring only the most reliable markers contribute to the analysis. Once prepared, the genome-wide scan commences, identifying potential associations between specific SNPs and the concentrations of the plasma biomarkers in question. The strength of GWAS lies not only in its broad scope, encompassing the entire genome without prior assumptions of where variants may lie, but also in its statistical power to detect even subtle genetic influences. By leveraging this approach, the study revealed how specific SNPs exert significant control over plasma concentrations linked to the cow's ability to manage metabolic stress. These findings hold profound implications for dairy farmers and the agricultural industry. Understanding which genetic variants influence biomarker concentrations provides a genetic roadmap for breeding strategies. By selecting these advantageous genetic traits, the industry can develop cows with heightened resilience to stress, which can translate to improved health, well-being, and productivity. This genetic resilience can also lead to better adaptability to environmental fluctuations and stressors, offering a sustainable approach to enhancing animal welfare and agricultural efficiency. Thus, GWAS illuminates the path of genetic influence within bovine biology and paves the way for practical applications. It empowers breeders to fortify their herds against the multifaceted challenges of dairy farming. The lessons from such studies reaffirm the crucial role of genomics in the ongoing quest for sustainable and resilient agricultural practices.
In the kaleidoscope of a cow's life cycle, the transition period stands out as a time of adaptation and transformation, marked by profound physiological upheaval. Spanning 3 weeks before and after calving, this phase poses an intricate web of metabolic stress and heightened vulnerability for dairy cows. The transition from gestation to lactation demands a recalibration of the body's resources, challenging even the most robust bovines. During this critical juncture, the dairy cow's body experiences a whirlwind of changes in energy balance, nutrient redistribution, and immune functioning. Such an intense period necessitates an equally robust genetic adaptation, where the orchestration of responses can pivot a cow's trajectory towards stress resilience or susceptibility. The genetic blueprint mapping these essential plasma biomarkers, such as peroxynase and gamma-glutamyltransferase, is the conductor in this symphony of metabolic shifts. The study's findings unveil the genetic control exerted over these biomarkers, offering insights into improving cow health management strategies. Dairy professionals can breed resilience by identifying the SNPs intricately linked to stress response during this tumultuous period, enhancing health and productivity. Implementing these genetic insights, alongside tailored management practices, promises to mitigate stress-related repercussions and bolster the overall well-being of dairy herds. Emphasizing genetic selection for robust biomarkers sets the stage for a future where dairy cows are better equipped to navigate transition challenges. This approach could anchor cost-effective interventions, fostering resilience and ensuring a seamless metamorphosis from pregnancy to productive lactation. The road to managing transition stress is paved with understanding and leveraging genetic control, guiding the herd toward healthier margins and greater sustainability.
By weaving genetic insights into the fabric of breeding programs, dairy farmers can pivot towards a new era of resilience and sustainability. Utilizing plasma biomarkers as genetic beacons presents an enticing possibility: the ability to breed cows that withstand stress and thrive amidst it. Imagine a herd where each cow is a paragon of resilience, capable of maintaining productivity despite the environmental and physiological stressors inherent to dairy farming. Why does this matter? Genetic selection for resilience traits, spotlighted by biomarkers such as paraoxonase and glynglutamyltransferase, offers the path to cultivating a robust herd. These cows have an innate ability to recover rapidly from stress, maintaining health and productive yields. This resilience translates into fewer medical interventions and improved survival rates, thus significantly reducing overhead costs. Moreover, the benefits compound over generations by embedding resilience in the genetic lineage. Each third-generation cow possesses the genetic makeup for resilience and a legacy of improved metabolic efficiency. Over time, this approach buffers the farm against adverse conditions and contributes to a more predictable and stable output. Financial sustainability. From a financial perspective, genetically primed cows that can cope with stress can mean longer productive lives and potentially increased milk yields. Reducing turnover can lead to substantial savings, with the cost of replacing cows averaging thousands of dollars. Enhanced resilience also leads to more consistent production levels, allowing for better resource planning and management. The ripple effect of such genetic selections means survival and profitability, an endgame every farmer can support. By adopting genomic tools to pinpoint and amplify these traits, dairy farmers invest in a future where stress-induced dips in productivity become anomalies rather than the norm. This strategic maneuver steers the farm toward short-term gains, long-term sustainability, and profitability. It is the blueprint for a resilient dairy sector, built on the genetic foundation of biomarker-driven breeding strategies.
As promising as the genetic approach to enhancing stress resilience in dairy cattle might seem, it is not without its obstacles. One of the most significant hurdles is the sheer scale of study required. The complexity of the genetic architecture involved in stress response demands extensive data from large cohorts of cattle, spanning various genotypes, management practices, and environmental conditions. This, in turn, requires considerable resources and collaboration across institutions and countries. Moreover, integrating genomic data with epigenomic and metabolomic information introduces an additional layer of complexity. While genomics provides a blueprint of potential, epigenomics and metabolomics offer insights into how genes are expressed and interacted with in the real world, contributing to the animal's phenotype. Synthesizing these vast datasets into a coherent framework that can guide breeding programs necessitates sophisticated bioinformatics tools and methodologies, which are still under development. Looking forward, the potential for future research is immense and promising. Technological advances continue to decrease the barriers to large-scale data integration. Genomic tools like CRISPR and more refined GWAS can offer unprecedented precision in identifying genetic variants that confer resilience. As our understanding of the interplay between an animal's genome and its environment deepens, we can enhance the resilience of dairy cows and craft breeding strategies that align with sustainable agricultural practices. The roadmap to a more resilient dairy cow is complex and fraught with challenges, but the potential reward, a robust, sustainable dairy industry, makes it worthwhile.
As we delve into the remarkable genetic roadmap guiding dairy cow resilience, the pivotal role of plasma biomarkers emerges as a beacon for sustainable farming. By highlighting G-glutamyltransferase, paraoxonase, alkaline phosphatase, and zinc, we've unlocked genetic clues that could reshape how we approach metabolic stress in dairy cows. These biomarkers, underpinned by heritability and genetic associations, promise to enhance cow productivity, health, and adaptability. This journey into dairy genomics isn't just about understanding, it's about transforming the industry. As we embrace these insights, one must ponder, how will these genetic advances redefine dairy farming, ensuring a future where resilience and sustainability walk hand in hand?
Thank you for tuning in to the Bovine Podcast. We hope you enjoyed today's insightful discussion. Don't forget to subscribe, share, and leave a review. Catch you next time on the Bovine Podcast, where bovine expertise and community come together.